Okay, welcome back. We're going to continue with chapter 10. And we're going to go to question 10. Not doing this one, and we're going to need a lot of room. So I'm just going to start question 10 right up here. I had to make these worksheets pretty quick, so I didn't really realize how little room we had. All right, well, high levels of cholesterol in the blood are associated with a higher risk of heart attacks. Makes sense. Well, using a drug to lower blood cholesterol levels reduce heart attacks. The Helsinki Heart Study, no idea what that is, recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. See, a lot of these AP questions just give you a lot of nonsense, and the numbers are hidden in, so you kind of got to bear through it. The volunteer subjects were assigned at random to one of two treatments. 2051 men took the drug Gemfibrozol, all right, to reduce their cholesterol levels. Control of 230, took a placebo. During the next 5 years, 56 men in the treatment group and 84 men in the placebo group had heart attacks. Not good. Part A, is there a difference? Is this difference statistically significant at alpha equals 0.01? All right, so we're not doing a confidence interval anymore. We're doing a hypothesis test. State. So our HO, so let's do this. This is going to be 1, and the control group, that's going to be 2. So for HO, is the true proportion equal 0? And then it wants to know if it's lowering it. So that's why it's less than 0. You could also say, does P1 equal P2? And is P1 lower than P2? Same stuff. But usually the AP will write it like this. So that's the state. All right, so plan, 2 sample, Z test for P1 minus P2. So the data have to come from 2 groups in a randomized experiment. So the data have to be randomly assigned to 2 groups in an experiment. Yeah, so it's going to be randomly selected if they're selecting people from the population, but this is an experiment, so they have to be randomly assigned. And these groups are independent because there's no one person in both groups, so you don't even need to say that. All right, next, 10%, you don't need it. It's an experiment. You don't even have to write what I wrote. Number 3, large counts. So once again, for the large counts, it's going to be N1P1, N2P2. Now N1P1, so let's see, what is, all right, 251 and 56 men. All right, so here's where my eyes go across. All right, so P hat 1, let's see. 250 men took that drug. Wait, 2051. Now, during the next 5 years, 56 men got a heart attack. Okay. And then P had 2, 2030, and 84. So really, you can just look at the numerators of these for the large counts, because 56 over 2051 is 0.027. So if that's P1, and I'm doing N times P1, well, times that by n, you get 56, which is just the numerator. But either way, however way you want to do it. Oh, let's see. So I get 56, and then 56 minus 2051, 1995, 84, 1946, and these are all greater than 10. All right, state plan do. Okay, so here's the do part. We got to have our test stat, so we're using z. It's going to be p hat 1 minus p hat 2 minus p1 minus p2 over the standard deviation. So we got p bar, q bar, p bar, q bar, and 2. What is p bar and q bar? They are called the pooled proportion. So the pooled proportion means you take all the people that had heart attacks, divide it by all the people. I'll show you this in a minute. Which is that. So it's basically we're pooling our results. Because if we're assuming that the treatment group and the control group are the same, then I should just pool my data. How many people had heart attacks? All right, now, the pooled proportion turns out to be 0.0343. So P1 minus P2, so that's going to be this value minus this value, which is 0.0414. All right, so 0.027 minus 0.0414 minus, that's 0. P1 minus P2 is 0. If they said the different, is the difference 4 or 40%, then you got to put 40% there. But usually it's always 0. And for this, 0.0343, 1 minus 0.0343 over 2051. That's long. But let's do this. All right, calculator, stat test, 2-sample z-test, 2-sample z-test. Let me just got to put the data in. No, stat test, 2-prop z-test, 2-prop z-test, 2 proportions, 56, 2051. Then you copy the HA. Enter. So here's all the info. So that's the test stat, p-value, p hat 1, p hat 2. That's the p pool. Either an average over it. Some books use a little c down here. Some books just use a caret, whatever. So my ZTS is negative 2.47. So to find the p-value in the center is 0. Well, actually, these are z-scores. So that's going to be 0 anyways. But here's negative 2.47. It is a left-tail test. So that's, and we're dealing with the test stat. So that z is less than negative 2.47. Norm CDF, negative 99, negative 2.47, 0, 1, and I'm just going to copy it right from the calculator, 0.007. So conclusion, since the p is less than alpha, we reject HO. So we have convincing evidence perfect. Interpret the p-value. I'm not going to do that. You guys can go look that up. What type of error could you make? Well, if we're rejecting HO, HO might have been true, so that's going to be a type 1. All right. So that's it for that question. And I'm actually, let me just interpret the p-value on this page. So remember, p-value assuming HO P1 minus P2, 0 is true. I'm going to do it like this. That value is the P1 minus P2. That's the 0.273 minus 0.0414 of the numerator, divided by this standard deviation. That's that. So what's the chance I would find that or less in the two groups? Proof of the mean and the standard deviation formula. Well, let me just show it to you. You don't have to know this, but it always goes back to random variables. So two random variables, if you subtract them. So if we're doing p hat 1 minus p hat 2, it's mu of p hat 1 minus mu of p hat 2. And the mu of p hat 1 is just p1 minus p2, so that's the mean. Standard deviation, when you subtract them, you're actually adding them, or variance. So when you're doing these two, it's just the variance of them. Now in chapter 6, this variance was this formula plus this formula. Then you undo them, you get this. So then the standard deviation would be the square root of that. So they come from somewhere. All right, let's talk about the sampling distribution for the, okay, so you pool with hypothesis test when you're dealing with two proportions. Only. You don't got to pool with the confidence interval. So sampling distribution for the difference of two means. So with this situation, you got two populations. So you grab a sample from this population, find the average. Grab a sample from this population, find the average, subtract them, plot it. So, they don't have to be the same size, but, N1, find the X bar, take another sample from here, it's population 2, so N2, X bar 2. Then we subtract these results. and we plot them. So we have all these different x bar 1s minus x bar 2s. And we do this a billion times. So we're going to have all these results, and it ends up being either normal or approximately normal, depending on if the populations are normal or not, and the n is greater than 30 for those. So, all right, the mean of all of these is just mu1 minus mu2, because this statistic is an unbiased estimator. So the standard deviation is this. If you think about it, we kind of did that in chapter 6. And then we're adding it, so we get this one too. So this has to be, this is the 10% for both samples. And the shape, all right, so the shape of x bar 1 minus x bar 2 is normal if both pops are normal. So you could have one or the other with this one. If it's neither of those, then we don't know. So they both have to be normal. Or like if this one's normal, this just has to be greater than or equal to 30 or vice versa. But if one of those isn't normal or greater than or equal to 30, then we are SOL. And I am assuming you know what that stands for, because when I say it, it means soiled and out of luck. Is Sean Stack here today? All right. Anybody have any questions? Anybody? Evan? Nope. All right. Confidence interval for mu1, mu2. It's this formula. Now we're dealing with mean, so it's a t critical value. S1 squared, n1, S2 squared, n2. Degree of freedom. Well, okay. With the degree of freedom, it's the smaller of n1 minus 1 and n2 minus 1. So if n1 is 40 and n2 is 50, then 39 and 49, so the degree of freedom would be 39. Okay, so, or the calculator gives a better degree of freedom. Now the formula for that degree of freedom is a disaster. It is this. A lot of fun, especially in the 80s when we didn't have calculators. So I would always write down the calculator's degree of freedom. But if you find the p-value with this degree of freedom, it'll be slightly off of the p-value with that degree of freedom. So whichever one you state, you must state the correct p-value. And never pool with means. Sometimes you do pool with means when you assume the variances are equal, but that's not in this course. Conditions. So the first one, they have to be two independent random samples Or it can be, you know, 2 groups from a randomly assigned experiment. Next is going to be 10% for both pops. Oh, actually, I should go back here. So we could also graph the sample data, because we're dealing with a t-distribution. So for each sample, if one sample looks okay, you know, without skew or outliers, we're good. If the other sample looks okay without skew or outliers, we're good. So we can use those samples to kind of generalize and say, all right, if those samples are okay, the population is going to be okay. Anybody bored yet? I am bored out of my mind doing this. I didn't realize how boring math was without doing it with other people or an audience, so missing you all terribly. And yeah. All right, hypothesis test. So HO is usually this. HA, you know, whatever those symbols are, depending on the problem. The test stat is this. It's usually 0. So 2-sample t-test, and in the confidence interval, it's 2-sample t-interval. And then degree of freedom is the same. So the smaller of n1 minus 1, n2 minus 1, or always use a calc. I don't even know why I'm giving this to you, but, well, actually I do know why I'm giving it to you, because if the AP wants to be tricky and do a multiple choice question where you aren't able to plug the data in your calculator, you're going to go with that degree of freedom. All right, I'm going to stop here.